Record button. Okay.
Okay. All right. I will start sharing slides then. So yeah, like Matt said, I am currently with technically OU and CIMMS, the other CIMMS down in Norman, and then NOAA/OAR/NSSL. And I'm going to talk to you a little bit about my research using multi-radar, multi-sensor data down here. So, but first I will share a little bit about me. Like Matt said, I got my bachelor's in science and meteorology from OU in 2015. When I started here, I started at as an undergrad research assistant in 2013 with OU CIMMS and NOAA/OAR and NSSL. My first project with them was actually working on the severe hazard analysis and verification experiment, which is known as SHAVE. And essentially what we would do is anytime it would storm during the summer, we would call people at their houses and ask them if it hailed after the storm went by. And this allowed us to create a complete swath of reports, of hail reports. And so it's actually one of the most high resolution hail data sets out there. And I actually use that in my research today, but I'll get into that a little bit later. And then my second project after that was working on the multi-year reanalysis of remotely sensed storms, which is known as MIRS. And that's actually what I work on now, now that I've come back to CIMMS. So most of my talk is actually going to be discussing that, so I'm not going to go into details. Actually, my first day, well, my first week at SHAVE, we got to do a damage survey on the Shawnee, Oklahoma tornado, and on our way back is when actually we saw the Moore tornado. So as actually my first tornado was the Moore tornado in 2013, which you can see in that picture on the right. So after I graduated from OU, I went to Wisconsin, and I had a research assistantship with the Northern CIMMS and SSEC. I got there in the first week of July, and they're like, hey, do you want to go on a field campaign? And I was like, sure. So literally a week later, I got to drive back to the plains and go back to Kansas and hang out on the Spark and launch weather balloons and hang out with the ARI for that. And originally my research was supposed to be doing some validation studies with the ARI, but it got switched up, and I actually did a validation study with the water vapor sensing system, which is a commercial or a moisture instrument that's on commercial aircraft. And so I did that using National Weather Service radiosondes. So that was super fun. I loved grad school. So I was like, I loved grad school. I got to travel a lot when I was in grad school, and I was like, let's move west. So I actually, 3 days after graduation, moved out to Montana, and I started my PhD in ecology and environmental sciences at Montana State University. This bottom left image is actually the view from campus, and that right picture of me is on top of that tall mountain. So I worked all summer working on research. I was looking at land atmospheric interactions and climate change in the upper Missouri River Basin. It started snowing. It actually snowed the day I moved, and then we got 6 inches of snow the day I moved into Montana, and then it started snowing again September 17th, and we got 6 inches of snow that day. And I really wasn't loving my research. I honestly can say that I chose the program based off of the location, and I've found that if I'm not super passionate about something, that I'm just not motivated to do work and stuff. And so actually after 2 months after starting my PhD, the classes anyways, I actually left, and it's one of the better decisions I think I've made in my career for me personally. I moved back home. I started applying to jobs, and that's actually how I came back to CIMMS. There was a position open. I applied to it, and I was like, wow, that sounds like a lot of stuff that I have a lot of experience with from undergrad, except now I know how to code. And so I got it, and I've been here ever since. Right now, like I said, I'm a research associate with CIMMS, and my job is managing the MIRS data set, which includes all of the data processing and all the derivative research. including managing a team of undergrads who also do research using this data set. And I also advise two senior capstone groups this year. When I have time, also I do a lot of hail size prediction using machine learning. One of the perks of being in research, I think, is getting to travel for conferences. On the bottom left is actually my first conference after I had started at CIMMS. And I got to go to Vermont for the Severe Local Storms Conference. Why they had a Severe Local Storms Conference in Vermont in October, I don't know, but I got to see the fall colors and the mountains. And instead of showing you pictures of me presenting, I'm going to get to show you pictures of cool places I've been after the conference or before the conference. In 2019, I got to go to AMS in Phoenix, and actually a couple coworkers and me decided that we're going to backpack to the bottom of the Grand Canyon and back. So that's me at the bottom of the Colorado River. And later in 2019, I got to go to Nara, Japan for the AMS radar conference. And Nara is actually known for all of the deer. They're like sacred in their culture, and you get to feed the deer. They actually can be a little aggressive if you don't feed them fast enough, which I also learned. But you also can pet them, and I got to spend a whole week in Japan after the conference, and it was amazing. And then last year I got to go to Boston for AMS again, and I actually broke my ankle the week before, so I scooted around Boston, which was kind of difficult on like their cobblestone streets, but it worked. And then I'm going to switch. How do I stop sharing? To part 2. All right, so that's about me, and now I'll talk about the multi-year reanalysis of remotely sensed storms, or MIRS. Not MIROS. I actually called it MIROS for like the first 3 months I started working on it, and I was very wrong. But MIRS is a reanalysis of the WSR-88D radar network using the multi-radar, multi-sensor framework. What is that? The multi-radar, multi-sensor framework actually takes all of the single radars across the country and merges them with the surrounding radars to create a 3D volume, a 3D radar volume across the entire CONUS. And it also is merged with near storm environmental model data to create other products that are useful. This went into operations to National Weather Service operations in, I think, 2014. And so the goal of this project was actually to go back to the beginning of the radar data set that we have and redo all of the radar into this new system, so we have a complete coverage of the entire CONUS. So this project started in 2012, and after several rounds of fixes, which I'll go into a little bit of detail later, it finally finished processing in 2018. Currently, the database is about 80 terabytes of data, and I am constantly adding more stuff to it. I'm actually uploading data as we speak. So it's a really intensive project. It involves a lot of processing. The domain itself covers, like I said, the entire continental United States, and it runs from April 22nd, 1998 through 2011. The beginning date is because of the lack of model data before that date. So that's where we had to cut off the beginning of it. We have radar volumes about every 5 minutes, and then a spatial resolution of about 1 kilometer in the horizontal. And then the vertical resolution staggers, and it's actually 250 meters from 250 to 3 kilometers, and then 500 from 3.5 kilometers to 9 kilometers, and then a kilometer from 10 to 20. And that's actually shown in this like vertical diagram on the right, is kind of an approximation of what that would look like vertically. So how do we process all of this? So to do the merging of the radar data into this MRMS framework, you actually have to process the single radar first, and then you merge all of those single radars together. To give you an idea of how complicated this is we have our MIRS storage device over here on the left, and then each date has all of the radars shipped out to all of our processing machines, which at one point we had like 26. I think we're down to like 16 now. Just because they're old machines and they're dying. And then on each one of those machines, the single radar gets processed, and that includes going at this top diagram here, where we do the conversion to a .NET-CDF file format, we do a reflectivity quality control, we do another reflectivity quality control, and then we de-alias the velocity, and then we calculate the azimuthal shear, which is the rotation within a storm. So after all of those single radars are done processing for a day, it gets sent back to the same computer where all of those single radars meet, and then the merging can kick off. And then when the merging is done, that whole file, tar up file, gets sent back to the data system or the data storage. And somebody has to constantly be monitoring this, because the single radar can fail at any point, the merger can fail at any point, and you have to have somebody monitoring that to restart it if it does fail. So like I said, it's really intensive, and that's how I actually got started on this project. Was I was the person who sat there and watched it and made sure it was actually running. The second part that goes into this is we have manual quality control. The operational MRMS system doesn't have this, and that's why this is like the scientific data set that if you are doing research, this is what we want you to use, because there's going to be a lot of things wrong in it. And I, as the person who also quality controlled it, I can tell you that there are a lot of things wrong in it if you don't take care of them. So what we would have, there was like a team of 5 or 6 of us who would sit there and we would go through the daily maximum accumulations of mesh and then of ash shear, and we would find out what was wrong. We would identify where that bad radar was, and when we found a bad radar, then we would have to go into the single radar data and then find which specific volume was causing the error. And then on the top right here, you can actually see that that's an example of a bad volume, and like, because that is, I think 65, 70, no, sorry, 90, I can't read that far, 90 millimeters of mesh, which is the maximum estimated size of hail, it would actually blow out the rest of the weather that was happening. And so you would really be able to see it. And so you would have to go in, identify that one bad radar volume, sometimes 2 or 3. And if there was no actual weather happening when this bad stuff occurred, then we would just remove it. And then we would have to reprocess it, which includes everything that I talked about on the last slide. And there's a lot of things that are like, if there's just a little bit of a blip that shows up at 90, millimeters when there's nothing actually happening, that can add up over a 14-year period. So another example of that is this bottom image here along the coast of Florida, where there's beam ducting from Key West. When it hits the coast, that shows up a lot. And if there's actual weather happening, we can actually remove it. And that's the example from Duluth. This is actually a yearly accumulation of mesh, and this ring shows up because there were actually storms happening over a 3-day period, and this ring just kept showing, like just little spots of it showed up every once in a while, but we couldn't remove it because the storms are actually coming through. But over a several-day period, that accumulated to be a full ring, even though the individual volumes only had little specks. So it's a very intensive process, but we get to do a lot of really cool things with it. And it includes a lot of different products. So the products that are included in mirrors include composite reflectivity, that 3D reflectivity volume that is actually created, reflectivity at the 0, -10, and -20 degree isotherms, reflectivity at the lowest altitude, 0 to 3 and 3 to 6 kilometer azimuthal shear, and that's just the total column, or the maximum of the total column right there. Maximum estimated size of hail, which is mesh. We have the severe hail index. We have vertically integrated liquid, and then we have 18 and 50 dBz echo tops. And then in the last year, I've actually added 40 dBz echo tops, and then the height of 18, 40, and 50 dBz above the melting level. So the rest of my talk is actually going to be discussing all of the finished and current projects using mirrors. So a couple of years ago, one of my colleagues did a brief study, a brief reflectivity climatology for AMS, and he investigated the seasonal and the monthly trends in reflectivity at -10, as well as the diurnal and geographic variations, and then also ground clutter variability. So up on the top right, you can actually see like the seasonal distribution of the reflectivity at -10, and then on the bottom right, we have the maximum DBZ values at -10, split up by month, so you can kind of see how it gets stormy during the summer and then kind of tapers off into the southeast during the winter. And then on the left, I think is the coolest thing is that's from Amarillo, Texas, and you can actually see the wind farms, which are in the top part of that image. And then all of those lines coming from the center of the image are actually interstates and highways. And those kinds of things, like I said, they add up over a period of time, which kind of makes your data set, it makes this data set very complicated when you're looking for stuff. Another project that we've done, this is actually one of the things that I did as an undergrad, was the rotating storms climatology. And initial results from this project, which I presented at in 2014, showed that there was actually an inaccurate range correction within the linear least squares derivative method of calculating the azimuthal shear. And so that caused us to update the algorithm that's used to calculate that, and they did that in 2017, and then actually in 2018 we started doing the climatology that I had done in 2014. And I just realized that says left and that's the right, but the picture on the right is the maximum accumulation of the azimuthal shear above the 0.1 threshold for azimuthal shear. And then we've done a lot of testing to filter the settings to capture the strongest rotation. On the left, on this bottom image, is the raw data for azimuthal shear for a 24-hour period. And then there is MHT is a multiple hypothesis tracking method, and that just allows you to connect clusters together over a time period. And using that kind of filtering, we were able to have like a minimal threshold and then a high threshold for the filtering. And so using the high filtering settings, which is what's accumulated on the right, we're able to almost get tornado tracks from that, which is the goal of that. So another thing that we have worked on is the maximum estimated size of hail climatology. I presented this in 2018. And so on the left picture, we have the maximum accumulated mesh for the whole MERS data set. And then on the right, we have the counts. And so it just shows the spatial occurrence of where we would expect hail to fall. But it also shows that there are limitations using mesh thresholds for the hail size classifications, which has actually led us to a lot of my current research, which is using hail size prediction using machine learning. And so using that shaved data set, which is a much smaller data set than the MERS data set, but we have all of those hail reports that we can pair up with the radar data. We can get a vertical reflectivity profile with a single radar or with the MRMS radar data, and with or without dual pole variables, and the near storm environment data. So we have all of this information, and we have a validation data set, and we can throw that into machine learning models to test what we can get out of them to see how they predict hail. And so we've tested this with the SHAVE data set, and then we've also tested this with the storm data hail reports from like SPC, and using the MERS data instead of just the single radar data. And so our results have shown so far that the machine learning predictions have a large spread similar to the mesh algorithm, which is what is used currently with the Weather Service with all of our tests. And so, but our machine learning models do a little bit better, but not enough to say that this is technically better. And one of the perks of using the SHAVE data set is not only are there maximum size of hails, but there's also the common size of hail, which is not something that normally is reported when you call the Weather Service and report hail. And so all of our studies have found that the common hail size is actually much better because it's not like the outlier and the extreme. So we're continuing to work on this. I actually have a student who is working on this, and we're hoping to get a paper out on this in hopefully this summer. And then, yeah.
Yeah, I was just wondering, to understand that your previous plot, can you take this downward slope and then fit a line to it and say, well, if you really want to do a better job at doing large size hail prediction, then you can use that correction. Is that can you use the slope to get a correction, or?
You could, but we found that like essentially it is kind of because this is like the deviation, so it's the predicted minus the valid. But when you get up to those higher extreme hail sizes, usually above 2.5 inches, there's just not enough data points to even continue that line. And as you get higher, it kind of curves, which is really, really frustrating sometimes. So it's not a 1-to-1 ratio exactly in hail size prediction, which is why it's such a complicated problem. And it's definitely something that we're continuously trying to fix to see how much data do we need, because like a lot of, technically with machine learning, you need millions of data points. We don't have millions of data points in weather. That would be an ideal situation, but and there's time discrepancies and spatial discrepancies, and that's what makes hail hard. But it's something that we've tried and hasn't worked, unfortunately. So does that answer your question? Okay, so continuing with the hail, I have another student who's working on a radar-based hail climatology using machine learning, and so we found that like the point just where you have the hail fall and grabbing the reflectivity profile from that is just not enough, and mesh alone isn't good enough for a hail climatology, which I showed 2 slides ago, and so the goal from this study is to develop a hail climatology using 1-hour swaths, which would actually be, it allows better size discrimination rather than just using like an X threshold. And so how we create these swaths are we accumulate mesh for over an hour-long period, and the top right kind of shows how this looks. And so you have like a single timestamp on the left, and then the hour accumulation is that middle image, and then from that you get this cluster or an object. And then from that, we can pull all of the radar fields and the near storm environmental model data, and that is our input for the machine learning models. And we have just started really testing this within the last couple of months. And my student presented this at AMS, and we'd really only run like 2 or 3 models. So we're continuing to run those, but this has actually shown the best predictions when using the lowest spread and actually the most accurate prediction so far. And so our goal for this is we've been testing all of this on the SHAVE data, and then we're going to apply it to the MIRS data set as soon as the model is fine-tuned, because playing around with 14 years of data is not easy. It's a lot easier to play around with a very small data set and then fine-tune it and then upscale it to a bigger thing. So with that, I'm going to move to part 3 of my slides. Share. That didn't work. Cool. So I have another student who is working on a very similar methodology project for, instead of using it for hail, we're doing it for just a general storm climatology. So instead of creating the swaths using mesh, we're using the EchoTop products, and just again creating the 1-hour swaths, and then we're going to pull those attributes from the radar data set and the model data set and use those to feed into machine learning. But doing this project, that actually ended up creating us, allowing us to create 4 new products for the entire MIRS data set. So that's when we added the 40 dBz EchoTop, and then the height of 18 dBz, 40 dBz, and 50 dBz above the melting level. And that actually only took a couple of months to run, which was really nice. And we have found that this is probably going to be another way to quality control MIRS in the future rather than just using mesh and ash shear. And then this is a really big project that we've been working on. This is storm clusters and the attributes from it. So from the entire 14 years of data, we have created clusters using the segmentation settings that are operational within the Weather Service. And so I don't know if you've heard of the Prob Severe model, but that's actually was created at UW-CIMMS. And they have a way, it's like a K-means watershed technique of segmenting clusters for storms. And using those clusters, we've run that setting on all 14 years of data. So we have millions and millions and millions of clusters now for severe storms, essentially. And we've paired all of those clusters with all of these storm data reports, so hail reports, wind reports, and tornado reports. And we're pairing, those paired data sets can be thrown into machine learning models, which I have a Capstone group or a senior Capstone group working on right now. And those machine learning models can help us predict convective threats for probabilistic hazard information. And so up here on the right, the top right shows, this is just for April of 2011. But you can, this data set is really interesting because you can separate it into fun categories and see what kind of distributions you get with these clusters. And so you can see that on the top left, we have low CAPE and low shear clusters, which is just, we cut the thresholds essentially in half. If it's below the 50%, then it's low, and if it's above, it's high. And then we have high CAPE and low shear on the top right. And then the bottom left, we have low CAPE and high shear, and then high CAPE and high shear on the bottom right. And then those colors are associated with the tornado rating that was reported. And then we have a very similar graph on the bottom right, except it's with hail and severe hail sizes. So not only does this allow us to have like a different way of viewing mirrors, it also creates a more user-friendly version of mirrors. Instead of having netcdf files and all of those different fields that you're pulling, it's actually just a CSV file with the cluster and we have over, I think, 1,200 attributes that have been pulled. So it's a lot easier to work with rather than just pulling down 80 terabytes of data. It's a little bit smaller. So hopefully we're getting that published within the next, or not published, but released in the next couple of months. And then I have another student who is working on National Weather Service warning characteristics, and she has paired all of the NWS warning polygons with storm data to create a verified versus non-verified data set. And then she's throwing that into machine learning models. This is another project where we've just started running the machine learning model, so it's not very good yet, and we're testing all these different methods. But she's also investigated the radar attribute distributions of the subsets of data. And so on the left, you have the low-level ash shear distributions for tornado warnings, with the far left being unverified, so no tornado report, and then the verified. So there was a report and inside the warning, and it's split up on the right side by a weak, strong, or then just a wind and hail report, but no tornado. And then on the right, we have that for mesh as well. So it's another really cool way to look at just how data is being distributed, and hopefully we can learn something from that. And so the goal from this project is to create a model to predict the probability of a warning being verified from storm reports, which would be useful for National Weather Service forecast offices, and giving them an idea of what they can, maybe if they can verify it or not, because it's also paired with land use data and population data. So if they want to verify a warning and there's nobody to call, they have a really good idea of that now. So the next slide, oh, there we go, is the future steps of MIRS. So MIRS currently only runs to 2011. In 2012, dual pol started being released. And so our next goal is to run from 2012 to present. And with that, we hope to also start merging dual pol products. So instead of just having a 3D reflectivity and the 3D ash shear, we'll also have 3D ZDR, correlation coefficient, all those fun dual pol products. And instead of running at a 1 kilometer resolution, we're going to be running at a 500 meter resolution, and then a 2-minute temporal resolution instead of the 5-minute currently temporal resolution. So On the right, it's actually, I'm showing echo tops with 50 dBz compared to the x-axis is the 1 kilometer, which is currently what we run, and then the y-axis on the left is the 2 kilometers, and then on the right side is the 500 meters. And so you can see there's a lot more agreement with the 500 meter than the 2 kilometer. And so anything really above 1 kilometer, you're getting probably some errors or some averaging issues. But we're really excited about moving forward with this. That's actually part of the reason I was hired back at CIMMS, was to work on this project and to get it moving into the next steps. But we've realized that none of our computers can currently computationally handle the processing that goes into these higher resolution mergers. And so we're looking into moving it into the cloud, which is requiring a little bit more work and money than we anticipated. So big steps, but a lot of things to figure out still. So as someone who has taken a little bit of a zigzag path and who works a lot with undergrads, I would like to share some personal advice with you, and things that I look for when I'm hiring students is, my first suggestion is keep learning. I want you, do whatever you can to keep learning. Teach yourself practical skills outside of the classroom, whether that be programming or machine learning or data science skills. Do not be intimidated by programming. I went into grad school and I did not know how to program at all. I originally started working with MATLAB, and I had a wonderful advisor who was very patient with me. And when I actually started my current job, everyone used Python and Perl, and they also use C++, which I still don't use. But once you learn one, you can learn another, and I promise it's not as scary. It's actually really cool when you figure something out. And when you're hired, take opportunities to learn something new or outside of your job description. I've actually gotten the chance to work with a lot of social scientists and helping in their experiments when they need help doing note taking or just stuff like that. And that helps you meet a lot of new people and just in fields that not necessarily you would normally get to work with. And like I said, I do a lot of machine learning. I would not consider myself someone who would be able to do that 3 years ago. I had the opportunity. My boss was like, hey, I'm going to work on this. Would you be interested in learning about it? So I actually spent several months self-teaching myself machine learning with a little bit of his guidance when I was confused. And then my boss was like, you need to get a certificate in this. So I actually have a certificate in artificial intelligence now. Just keep learning. It's just, you're going to learn so much more and be so much more of a useful person when you just keep learning. Another thing is just to apply to all the jobs that sound interesting, even if you don't meet the requirements. So I know personally from a hiring standpoint that we list it would be great if you had this, this, and this, and this, but realistically, we're just happy if you have 1 or 2 of those. It would be, wonderful if you had all of those experiences, but we don't expect that. And a lot of places are very similar. They would just really like if you were interested in that kind of a job, and if that you're willing to learn maybe some skills that you may not have. And then my boss personally wanted me to tell y'all that when you're getting an interview, that don't be afraid to go into detail about what you do. This is the time to showcase your skills with examples of your work. He was so adamant about this that he actually made me make a website for the research that we do. So having those kinds of examples that you can say, yes, I did this and this is how I did this, or that is something, that's a way to showcase yourself and make yourself stand out a little bit more. And the next thing I'd like to say is be flexible. Your first job is not going to have everything that you want. I promise you that. It's not going to be maybe in the greatest location, or it may not have the benefits that you want, or whatever that may be. Make sure you have a set of yeses, things you can live with and things that you can't live with, and then be flexible about everything that else. I know when I was personally looking for jobs, my definite yes, no is I have to have a rock climbing gym within 30 minutes drive. That's my personal hobby. I have to have a work-life balance. So like I would only apply to jobs that within 30 minutes I could get to a rock climbing gym. Like, which sounds ridiculous, but like it may not be climbing outside, but I can still, you know, do it in the gym. So just be flexible. And then this is my biggest thing is it is okay to change your mind about what you want to do. Like I was very set on Montana. I was going to spend 4 years there getting a PhD, and I was going to love the second of it, and I didn't. And I quickly was like, I changed my mind. And it's okay to do that. And you are the role or the driver of your life, and like you can only be the one who changes things if you're unhappy. So just be very conscious of that, and take time to check in with yourself to make sure that is something that like you continuously want to be doing. So with that, I am happy to take any questions on careers and research. I haven't had any experience anywhere else about mirrors, about big data, machine learning, career advice, etc. If you don't want to ask me a question in person, feel free to email me. If you're interested in working with the mirrors data set, we have a specific email there, mirrors@ou.edu. And if you want to play around with the data and just see what's there, all of our data is actually available online at that OSF website right there. So any questions?
Yeah, thank you for a very interesting and thoughtful and friendly advice too. And also the timing is perfect. You got this talk just perfect. There's some time for questions.
Yes, that was the goal.
So what would you recommend to do to try to like practice your coding or like build your programming skills on your own?
So I like to look at tutorials that are free online. One of the things I personally recommend to my students, because we actually like when they're running data and stuff and they want to get more work hours, we were like, hey, go work on your programming skills. And OU has this deal with like LinkedIn. I think it's called LinkedIn Learning, or it used to be called Lynda. And there's actually a lot of free tutorials online that you can look at through there. And it just takes you through like examples, and then would usually give you like a problem to try to solve. And if you don't have LinkedIn Learning, there's so many other free resources out there to like challenge yourself with. And that's like I would think that's like the biggest place to do that. It would be just some kind of online guide that they have, and they are free. Do not pay for them unless you're trying to get like a certificate or something.
Some other comments or questions? I've got a few. Maybe I could just ask one. I'm curious, with your dual polarization, does that mean that you could detect the melting level for the rain-snow interface? Is that right?
Yes. I personally only really work with severe weather, but we actually have another group who at CIMMS that does a lot of hydrometeorology stuff, and that's something that they've been working on, is creating melting level detection algorithms and stuff.
Do you also work with, my impression is that there's a group there that is trying to develop a better lightning data product. Do you have is there a plan to try to link your hail and radar reflectivity with lightning data, or is that?
Actually, yes, that's a project we're currently working on. We are like in the very beginning steps of doing all the data gathering and data mashing, so they're all together, and that's actually something that I'm going to be working on in the next couple of months.
Yes, Colleen. Go ahead, Colleen. Maybe you have to turn your microphone on.
Can you hear me now?
Yes.
wait, for some reason my permissions are just like, you don't have permission to turn on your mic, and I was like, I always do, so I don't
Oh,
know.
really?
Sorry about that. But my question is, so I've just been kind of looking at like, I'm doing undergraduate research right now, and I have kind of been thinking about grad school, but honestly, like the 2-year plus commitment to like one topic kind of scares me right now because I feel like I have so many interests. So I guess do you have any advice along the lines of like looking if I should just like look for like jobs in like a research field, because I like doing that. Like I think it's a lot of fun, but I think the whole thing of like committing to a grad school honestly really scares me at this point in my career.
So my biggest suggestion to you would be find schools that have teaching assistantships first, because that'll actually give you at least a semester or two to kind of see what's out there in your department. That was something that was suggested to me when I was first applying to grad schools, because I was like, I don't know really what I want to do. I actually applied to Wisconsin to do satellite research, and that is the exact opposite of what I did. So, I mean, my first thing would be definitely look into like teaching assistantships, because that'll give you a little bit more flexibility on choosing your research topic. My second thing would be, if you want to do a career in research, I would highly recommend getting a master's. A lot of places will not hire research positions without a master's degree, because that just shows that you have the capabilities to do research, usually because they're masters usually with a thesis option is usually always, you know, research based. But if you like research, like I think that the hardest part for grad school for me was actually doing the schoolwork, because I loved doing research, and that's something I learned in undergrad as well from having an undergrad research job. Was I liked doing research. I knew I wanted to be in the research field. And being able to stay in that after grad school was something that was really important to me. So if like I said, if you like research, committing to a topic and honestly, you really only commit to a topic for a year. Like your first semester, you're figuring out your classes. The second semester, you're really just starting to get into your research topic. And then the next year, you're spending doing the research, writing, and then you're done. And then maybe it takes 2.5 years, maybe 3, but it's really, compared to getting a PhD, like I can't speak on that, but I think that was more of the big scary factor for me, was committing to more than 2 years. I don't know if that makes sense, but I hope that helps.
No, it does. Thank you then, yeah, for that advice, because that really, it does help, so thank you.
And feel free, if you have more like questions in the future, feel free to reach out to me.
Thanks.
Anybody else have any comments or questions? Well, maybe you can think of another in just a minute. If I could ask another question.
Yes.
So for your 3-dimensional radar reflectivity data,
Yeah.
it looks like it starts in 1998 or so. Does it go through, does it include last summer?
Not yet.
Not yet. All right, that's fine. I could maybe try to pick a couple of older storms, but I've been really interested in the August 10th derecho that went through Iowa. I'm trying to look at it from a potential vorticity structure thing, because you know you have downdrafts and updrafts, and they tilt and twist vorticity tubes, and that's interesting to me. But wow, to be able to get 3D radar reflectivity for that storm would be pretty fun.
And that's one of the things, like the settings that we've been testing. Instead of just having azimuthal shear as a maximum, we're looking at having div and as shear, so you would get those varying things. But getting to that point there's a lot of computations that have to go into that, and we don't have that power locally at NSSL at the moment.
Well, it's a really great product. All these different things you're working on, this infrastructure development, I'm sure will become standards for, you know, like if somebody does a monthly weather review paper with mesoscale storm, they better use your data.
I
No.
hope so. And we actually just released the data itself in November of 2020. So having it out there in the public is relatively new to us, but we're really excited to be able to finally share it.
Well, does anybody else have further questions? Well, if not, that's fine. You could always contact Skylar at the email address there. And yeah, thanks everybody for coming. And thank you, Skylar, for a really nice presentation.
Thank you for having me.
Let's see if I can do it. I'm still working on
Thank
these
you.
bugs. Oh, here we go. There's the emojis. All right. Thumbs up.